All right, so now we're gonna do problems 20 through 40. I was gonna do 1 through 20, but I skipped number 20, forgot that it was there. And now I've had a chance to walk down the hall and back and clear my head, so hopefully that's gonna help with careless errors when the brain gets tired. All right, so graphing form. Well, I know one thing, when one of these is positive and one of them is negative, then I know I have a negative there. That's what I have learned by looking at the answers to these. So minus 20 becomes 20 over 10. That's minus b over 2a, so it's x minus 2 squared. And I know that a 0 gets me 5 over here. A 0 gets me 5. So I throw a 0 in here and I can see 20. I don't want 20. I want 5. And so I think that's my graphing form, minus 15. Now, I'm going to check it in case I was giving this as an answer key and I had time to check it, then yes, I would drop a 2 in. 4 times 5 is 20. That better be minus 40 or I've made a mistake. Yep, that's minus 40. So that's minus 20 plus 5. I think I'm okay. So I move on. What are the roots for this picture? Well, I can see the roots. I'm measuring from 8. I know I got to go further to the right and further to the left in order to hit a height of 0, which is here, right? I got to make this thing go in the other direction, sign change. So that's going to be some sort of imaginary answer. Because if you think these intersect, these two graphs intersect, I'm sorry, they don't. And so therefore, how far do I have to change? By 3 units. Oh, I'm down here. I got to change by 3 units, but I got a multiplication by 2. So I think I'm done. Why do I know that? Because I know if I put this in graphing form, I have everything here for graphing form. Y is equal to 2 times x minus 8 squared plus 3. If I set that to 0, you do the inverse operations. You do the minus 3. You divide by minus 3 divided by 2. You do the plus minus square root of minus 3 over 2, and I hope you erase the minus sign and you put an I there, and then you bring the 8 over. Minus 8 becomes positive 8. All of that, vertex, the A term, and within 5 seconds, you know the roots. Oh, isn't that a nice thing to be able to do? Yeah, it's worth practicing that. You'll save a lot of time down the road. X to the 4 minus 16, still causing a lot of trouble. Okay, at least we are getting to the point of saying x squared plus 4 times x squared minus 4. But the whole purpose that I'm asking this is if you see the difference of 2 squares. So if you write that and you don't see the difference of 2 squares, I guess you still haven't processed this concept. X plus 2, x minus 2. Don't let me fool you again, because I'm going to try to. And thus far, I have. It's been on 4 tests. Not many people seeing it yet. Any subtraction, any number minus another number, we'll call it A. Any number minus another can be written as the square root of n plus the square root of A times the square root of n minus the square root of A. Now, that had a difference of x, what was it? It was x plus x squared plus 4 times x squared minus 4. And we got that one to be x plus 2, x minus 2. Now, no one is asking you to factor that. Right? We're basically looking at integers when we're factoring, but there's no reason you couldn't have called this the square root of x plus the square root of 2 times the square root of x minus the square root of 2. That's its conjugate. All right, and that's going to get rid of the square roots. And we do that sometimes when we rationalize denominators. So it's a good skill to know. Working with conjugates. But no, but I'm not going to ask you to do that. You can leave it here. But yeah, can't leave it there. That does not tell me that you understand how to make this working knowledge. All right, so that one's done. And we talked about it a little bit. That one's done. So I can erase these now. All right. How do I solve this? I hope your brain does the following. Minus 18. Two answers. Minus 18 divided by 5. Plus minus the square root of 18 over 5. Imaginary. Move the, oh, that's it. We're done. There was nothing. That's already in graphing form. So 5x squared plus 18 is centered on the y-axis. I'm just moving x squared up 18 units and changing my y values by a factor of 5. So it's going up faster than x squared would. And I'm looking for when it hits 0. And again, that graph does not intersect this. So you are imagining it coming down in the other direction. How far do I have to go from 18 units? Gotta go down 18. All right, so that one's done. Two answers here. I still see one. I'm still seeing 77 over 93. I see that a lot. I wish I was seeing this a whole lot more. Okay, I can't use square roots on this because when I bring this over, I've created a rectangle where I have x times 93x minus 77. Geez, I'm having a hard time writing sevens. And that is equal to 93x squared minus 77x. So I have two dimensions, and if I want to make the area, which that's an area statement, 0, then I either get rid of the width or I get rid of the height. What value for x makes the height 0? That's the one we're missing. So what did I do? I factored it. I took out what's common, which is x. So I take an x out, and I hopefully make a connection to the geometric origin of this process. All right, here's another problem that causes me consternation. I lose sleep at night trying to figure out how to get folks to get this right. How to do bingo, bango, bongo. Now that seems simple enough, but probably the most important Algebra 1 concept comes out of this problem. Probably the most important one. And it is, I'm going to subtract a number that has two parts. I'm going to subtract the number 5. But I'm going to write that as a subtraction of two numbers. Why don't I say 2 plus 3 equals 5? And I want to get negative 5. I think I need minus 2 minus 3 to get negative 5. Which means that if I'm going to multiply a number, if I'm going to subtract a number with two parts, let's say the two parts are A and B. And if I'm going to subtract those two parts, I gotta understand the parenthetical nature of that calculation. It's got to be in parentheses. And I think I'm going to get two parts here. And we aren't seeing that. So what are the two parts? 5 times x minus 4, 5x minus 20. X minus 2 times 3, 3x minus 6. X plus 2 times x minus 4. I actually, bingo, bango, bongo, I want the bongo to be done later. Because you never know when you're reducing fractions if the numerator might have x minus 2 as a factor or x minus 4. So I'm going to hold off on that. Now, what does this become? 5x minus 3x, 2x, minus 20, minus a minus, minus a minus. I've got to do that distribution, which makes plus 6, minus 20 plus 6, all over x minus 2 times x minus 4. If I factor that, it's 2 times x minus 7. I don't see x minus 7 here, so you can leave it like this. But if you do multiply it, don't make a mistake. Okay, if you don't make a mistake, you get the check. But if you multiply and make a mistake, don't get the check. So feel free to leave it like that in this class. All right, that takes care of that. mx plus b. All right, so hopefully you're doing this. Minus 7/3 x plus 35/3. Minus 2 is minus 6/3. Then I hope you're putting the thirds together to get plus 29 over 3. There's your practice. multiplying a few fractions, adding and subtraction fractions, and you want to get good at it, then practice it. That takes care of that one. Squared, you should be able to do that in your head. 2 squared is 4. A to the 3 squared is A to the 6th. B to the 7th squared is B to the 14th. When I'm multiplying, you can think of this as x. Minus 5 times 2 is minus 10x, and you got to double it. So we have minus 20. X is A3, B7. And we also have to bring in a C. And I'm talking to you, and I'm really not thinking about the calculation. So let me make sure I did that right. Minus 10 becomes minus 20. Okay, I'm feeling good. And whenever you square, I don't care if it's positive or negative. If you square it, it's positive. And we get the binomial squaring. 25c squared. And I hope that you're doing that 10 seconds or less. I hope you're not having to write out parentheses times parentheses. That's gone. I hope I pushed join. Hope this is recording. I think it is. All right, cosine of A. Time to do some seed planting. I'm going to look at that angle in a minute, and I'm going to tell you my guess, and then I'm going to check Google at the end to see how close I am, because I've learned something in the last couple of weeks. All right, so I'm looking for the cosine. You need that x value. 25 minus 4 is 21. So you got the square root of 21. And that's 20 square root of 21 over 5. All right, you're getting pretty good at that. All right, I'm looking at minus 2/5, which is negative 0.4 divided by 1. That's the sine value, negative 0.4. And I know the other day I did the 30, 60, 90, right? 30 degrees, and I looked at pi over 6, which is 3.14 divided by 6, which is about 0.52 radius lengths. Right? And I know that this is a half, which is 0.5. That's almost 1-to-1. That's almost 1-to-1. And that's a 30-degree angle. Well, I got 0.4, negative 0.4. That means this is almost 1-to-1 range. Okay, and the sine function looks like this. 1 period. That's like y equals x. There's a 1-to-1 ratio for a while. And the closer you are to 0, the closer you are to 1-to-1 exactly. So I know my answer for an angle here is about 4/5. It's about 4/5. 0.4, right? How does that compare to 0.5? About 4/5. All right, and what's 4/5 of 30 degrees? Well, 5 goes into 36, 24. So I think this angle here is near minus 24 degrees. I certainly think it's near minus 0.4 radians. So I'm going to go to Google and I'm going to solve this. Well, that was good. The way my voice just cracked. I'm going to solve this. So how do I solve it? And that's where we're seed planting. I'm not hurting you by showing you how to solve this. I'm just giving you something to think about in future classes. You're going to see it again. Isn't it nice to see it once before you get there? So what do? I do the inverse of cosine to get this angle. Oh, that's a button on your calculator where this is stored. All right, I think it's going to give me answers in that vicinity, depending upon whether I put this in radians, or degrees. But I'm going to check it later, see how close I am to this. And then if it's divergent a little bit, then I'm going to, I might up this. I think it might be closer to minus 25, but I'm not sure. If it's closer to minus 23, then I'll think a little bit harder and figure out why I, intuitively had it wrong. But I want to be hopefully in this terrain. And if I'm not, I'm going to stop and go, where's my thinking faulty? And now I'm being a mathematician versus, just putting out the math, doing some thinking. All right, distance. I hope you're doing these in your head. 2 to 5 is a change of 9, right? Because you're going to square. 1 to 6 is 25. So that distance is a square root of 34. All right, perpendicular. Well, a minus, in standard form, a minus means this is going up, which means the perpendicular has got to be going down. All right, and what do we have? We have a constant, a k, constant spelled with a k, that's true. Yep, and constants don't affect rates of change. So I could have made that anything. It's the interplay of these. The interplay of 12x to 5y, then the original slope is 5 over 12. That tells me the perpendicular is minus 12 over 5. And if I wanted to go through hay there, x minus hay, why don't I say hay as hay? Because it's going to start growing now. There. Hey, there's hay out there. Yeah, getting a little squirrely. I hope you can read that. I'm not putting a lot of time into this one. This is a classic Algebra 1 problem. Y varies directly as x and inversely as z. I'm giving you x, y, and z. That's going to allow you to solve for k. Once you solve for k, put the number in there. Let's see if we can do it on our head. 4 times 4 is 16 divided by 2. I think it's 8. And then what can you do? Put in the new y, 24. And put in the z, 4. And solve for x. Done. I could have easily made a careless error there because I'm talking, not thinking about the computation, but that's the process. Yeah, so let's get back to our initial discussion in the first series of questions, 1 through 19. And let's write y equals 1 plus 22. I need that to be times 0, and I also need it to be times 1 in order to get the numbers 1 and 23 out of this. All right, how do I make a 0 out of the number 2? X minus 2. How do I get a cup-shaped graph? It's got to be squared. So that tells me I got to get the number 1 out of x minus 2 squared when I use a 7. And if I use a 7, I get the number 25. And I want that to be a 1. I think I can divide it by 25. That's the process. Now, I'm not going to write it from left to right like that, although it kind of looks like the first thought process for something called Taylor polynomials. I'm going to keep it in the y equals ax minus h. That's a linear. The second is ax minus h squared. The cubic is x minus h cubed with a whole lot more. But I'm going to get a standardized approach here. And if I do that, I've got x minus 2 squared plus 1. I know I'm going from 1 to 23. That's up 22. And when I put a 7 in, I get 25. And that's what we want to be able to do. And then we want the roots from that very quickly. The roots would be what? Subtract 1, multiply by 25, divide by 22, take the plus minus square root and add 2. All right, CIA, they're coming after you. And I think they might be. No, FBI comes after you. No, it's a different government agency. Watch out. Trying to get you to memorize the quadratic formula. Minus b over 2a. That's going to be part of it. Minus b over 2a. It's going to be there. Plus minus square root's going to be there. B squared, which is I, minus 4 times a times c. That was fun. That's now a and that's c. There's your quadratic formula. Notice the fraction bar under both terms. Under both. If it's only under one, it's wrong. If you forget the plus minus, it's wrong. If you get anything out of the order, it's wrong. And so that's meant to be just another way of approaching memorization of the quadratic formula. I will still derive it. I hope there's time. I hope there's time to derive it. I think it's a rite of passage. Try to derive it on your own. 18 and 12 have a 6 times 3 times y to the 4th times z minus 12. Sorry, minus 4 times 3. Y to the 6 is y to the 4, y squared. Z squared is z times z. What's the first rule of writing products? What's common? Well, I can see I didn't take out the biggest common factor already because I still have even. So I'm glad I did that. Right? These are still even. I made a mistake. What's common? 6 is common. 6 times 3 and 6 times 2. That's what I should have done. At least I caught it. What's common? 6. Y4. Z. I'm going to take out 6y4z. Then I'm going to build it back up to 18. Y4z, I've already got it. Minus, looks like I need a 2. Looks like I need a y squared because I took out the y to 4. Looks like I forgot to underline one of the z's, right? One of the z's comes out. Another one stays in. There's that product. Why am I writing this way? Because I'm tired of seeing people not putting the negative outside the radical sign as an imaginary square root. 50 is 25 times 2. One of those square roots is very friendly. That one is. So I'm going to bring a 5 out here. Now we don't put a 2 here, right? But 5 squared is 25 times the 2 that's left there tells me it brings me back to 50. All right, so looking at it again, can you see that becoming that? Can you see 25 hiding in there? Now, looks like I'm looking for the square root. Square roots work very nicely on even exponents. So if I divide that by 2, I get x squared 21 times. That means the square root of this is x to the 21. And 21 times 2 is 42, and I needed 43. I need 1 left over here. And 2 goes into 6 3 times, so I got to make this further over. So that's y to the 3. How do I check it? 3 times 2, 6, I'm done. Square root of z squared, z to the 1, 1 times 2, 2, I'm done. Okay, so that's kind of ugly. All right, enough said. Hope you're getting good at this. Hope you're saying x minus 2, that's positive 8. I need another 3. Critical number here is 4. If I put a 4 in, I should get a 3 out. If I put a 4 in here, I should get a 3 out to check it. 16 minus 18 plus 11. Minus 18 plus 11 is minus 7. I'm not getting 3 out, so I must have made a mistake. I like that. I got to get to 11. Right now I'm at 8. I'm at 8. 8 plus 3 is 11. I like that. If I put in a 4, I get a 3. 4 squared, 16 minus 18 plus 11. 27 minus 18. I'm making a mistake here. And I'm not seeing it. Let's start over. Let's start over. All right, so there we go. X squared is correct. This is minus 4x. Got to get to minus 6x. Minus 2 is certainly correct. 2 times minus 4 is positive 8. I got to get to 11. I got to go 3 more. And I'm doing something wrong, but I do not know what. Oh, how alarming. 4 squared, 16, minus 4 times 6. That's a problem. 4 times minus 6 is minus 24 plus 11. Major computational error by the old guy, which has now been caught. I don't have to do the video again. Yeah, minus 8 plus 11, 3. I'm going to move on now. So it's good to check certain problems that you know how to do, but sometimes you just don't do them right. Reducing. Well, what's the computation here based on? It's based on division. Seems like inverse operations are very important in math. And what's the inverse of division? Multiplication. So let's show this as a multiplication problem. X minus, X minus. I think we saw that before. Negative middle term, positive end term. It's got to be minus minus. Sure looks like a 2 and a 4. I'll bet you one of those factors is in the denominator. Oh, x times x minus 2. I don't think I have to multiply by x minus 2 and then divide it by x minus 2. I think that's going to leave me with x minus 4 over x. Well, that's not bad. What if I put a 5 in here? A 5 gets me, do I want to put a 5 in? Yeah, I guess so. 5 minus 4/5 gets me 1/5. So a 5 gets me 1/5. If I come over here and put a 5 in and I don't get 1/5, I did something wrong. 25 minus 30 minus 5 plus 8 minus 5 plus 8 is 3. 5 and 25 minus 10 is 15. 3/15 is 1/5. I'm moving on. Very helpful skill in math is seeing critical numbers. Now, that may have a strict definition at the calculus level, but at this level, I'm very loose definition, critical numbers. Critical numbers to me are seeing numbers at work. Seeing numbers at work. It's critical to be able to see something that works. So I want to get 3. All right, I can't let y equal 0. A lot of you let y equal 0 on the last test, and that was planted there to see if you would use 0, and you did, unfortunately, because division by 0 is undefined. Sorry, you just got a computation that's undefined, and the computation on the left is supposed to be 3. So I might work with this number, maybe 98. That might be fun. 98 gets me 1, then this has to get me 2. Well, I think I got 1 coordinate. I think I could maybe divide this by 2. Okay, so if I divide it by, divide to get it 2. To get it 2, I want what, 49? So if that's 49, it goes in twice. I think that's a 15. I'm sure there's more combinations, but I just asked for a couple of points. I just found a couple. Didn't have to work too hard. And what do you do with numbers? You plug them into the variables. So I look for some friendly numbers. Help you keep your eyes out for friendly numbers. They could be your friends. All right, so can you do this one in your head? Can you subtract 5? Keep that number in your head. Can you multiply by 4? Can you divide by -3? That's a whole lot different than doing -5, -5. You don't want to have to do that. Okay, and I'm going to get an argument from a lot of teachers about showing every step. I'm okay. I'm retiring. They can't find me. Intersection. What's the coordinates? Well, minus x squared plus 20. I don't know if you can do that yet, but that's that graph. It's x squared turned in the other direction and then lifted 20 units. There, I'm using the language of transformations, and that's okay. Because transformations is a pattern, and after I work with enough, I want to know patterns. All right, and so we've been working with it enough. I think I can start talking about patterns versus giving you the patterns and having you work backwards towards the organic creation of it. That sounds like I'm in a religion class. The organic creation of it. Y equals x. I think I got a couple of answers here. How do I find them? How do I find where this graph intersects that graph? Where the table values are the same? I guess if they're the same, then they're equal to each other. And now we find out if your Algebra 1 skills are okay or not. Because this is now a multi-step question. You had to graph it. You had to figure out, I'm setting them equal to each other. Do you have the skills to solve that? Hope so. Hope you can do that. Hope you can do that. Hope you can do that. I think -5 works. I think if I put -5 in here into y equals x, I get -5. I think if I put -5 in here and I square it, I get 25, but -25 plus 20, because I got to square first before I subtract. Does it look like they intersect over here at -5, comma -5? I think so. And over here, I think 4 gets me 4. You can take time with that. And you got to be able to do this skill in order to understand that area accumulation between the two curves. That's another whole period of study. And we started talking about that without you realizing it when I started adding layer after layer after layer after layer after layer on an existing square, going from a 2 by 2 to a 3 by 3. And that's net change. Got a lot more to talk about, be able to get from here to here. But if you want to, look at the video, the relationship between differentiation and integration, and it will give you a planted seed. And that's not going to hurt you. Planting a seed will allow your intellectual, conceptual awareness of calculus to grow. But you got to start a conversation. I just started. We'll keep talking about it. All right, off you go.